the fifth session for this short course El Niño en las Américas, proteger la salud y promover la resiliencia. Como les había
The Americas protecting health and promoting resilience. This is a course organized jointly by some organizations such as PAHO, the WMO, NOAA, the United Nations Office for Disaster Risk Reduction, and the Global Consortium of Climate and Health Education. This is the fifth session, and we're going to deal with vector-borne and zoonotic diseases. I'm going to be your moderator today. I'm Helen Padilla, and I am a member of the Unit of Climate Change and Health at the Pan American Health Organization. I'm also a part of the STEP program for the Inter-American Institute for Global Change Research. This session has simultaneous interpretation available in Spanish and English. You can change to your selected language using the button at the bottom of the page to listen in either English or Spanish. Next, please. This is the fifth session on vector-borne and zoonotic diseases, and we also would love to have you for the next one that will be on air quality. These sessions last for 90 minutes, and at the end of the session, we will have a Q&A session. Please write your questions as they come up in the Q&A section below in Zoom. Materials and the recording will be available in the website within 24 hours. Next, please. In this website, you will also find the slides for this course. I invite you to review the links for the previous sessions and at the maximum within 24 hours. Next, please. Okay, and also in the chat, we will be sharing a document of recommendations prepared by PAHO with short-term acute recommendations, and you can download them from that link. Next, please. In this session, we have two speakers. I'm going to briefly introduce each of them. Our first speaker is Rachel Lowe. He's an ICREA research professor leading the Global Health Resilience Group at the Barcelona Supercomputing Center. She has published articles on the risk for climate-sensitive diseases, and her work has focused on the viability of integrating seasonal climate forecasts in early warning system for infectious diseases in Latin America, the Caribbean, and Southeast Asia. Our next speaker, Ángel Muñoz, is a senior researcher at the Barcelona Supercomputing Center. He focused on the co-leads. He works on human migration, food security, undernutrition, vector-borne diseases, and lightning activity. We welcome everyone. And now I will give the floor to our first speaker. Rachel, please go ahead.
Thank you so much. Can you see my screen? Well, Thank you very much. Thank you very much for the invitation to contribute to this fascinating course. So today I will be sharing some of our research on trying to understand how El Niño and climate variation may impact the outbreaks of vector-borne diseases. So here we can see a graph showing us changes in temperature from 1850 through to 2023. And we can see that decade upon decade, the global temperatures have been warming dramatically. And particularly this year, up to September last month, we've seen unprecedented and record-breaking temperatures. And this is partly due to the signal we're seeing from climate change, but also we have the developing El Niño event, which is also contributing to particularly warm temperatures. And this has implications for the expansion, spread, and outbreaks of vector-borne diseases. If we take the example of dengue, over the last few decades, we've seen dengue increase from impacting around 9 countries in the 1970s to over 120 countries and more. We're starting to see emergence and outbreaks in places that were previously unaffected, including Europe. And the World Health Organization estimates that around half the world's population is now at risk of dengue and other diseases transmitted by the Aedes mosquitoes. And modelling studies have shown that if we're to continue on a business as usual trajectory, we can expect billions more people to be at risk of these diseases. So it's very important that we can both mitigate the impacts of climate change and also make sure we can develop strong adaptation strategies to be prepared. This here is showing how dengue has been spreading across Brazil. Brazil is one of the countries in the world reporting more cases of dengue than anywhere else. We can see in the first decade of this century, the distribution of the municipalities across Brazil experiencing outbreaks of dengue. And we can see these circles are showing areas in the south of Brazil and the Amazon where we had protected areas. So these are either protected due to cool temperatures or perhaps being more remote areas. But if we assess this data up to 2020, we can see that dengue has been spreading gradually south in the country and also into the Amazon rainforest. And studies have shown that this is partly due to warming temperatures, particularly in the south, which is allowing the mosquitoes to be able to survive for longer periods of the year and to be able to transmit the disease. And also we're seeing increasing infrastructure, allowing more connectivity between those areas in Brazil that experience explosive epidemics and the more smaller cities in the Amazon rainforest. Also in Europe, these unprecedented warming temperatures are allowing the Aedes albopictus mosquito, which is prevalent in many countries across Europe, to survive for longer periods. We recently published a commentary with colleagues in Greece who have found for the first time a large number of adult Aedes albopictus mosquitoes surviving over winter. And this coincided with the warmest ever recorded temperatures there. So this is a real concern about how the warming temperatures and changing climatic patterns are impacting the potential for transmission of these diseases in new places. Last year, we published a scoping review assessing the evidence of outbreaks of extreme climatic events in the aftermath of infectious diseases in the aftermath of extreme climatic events. So, for example, reports of diseases like dengue, malaria, diarrheal diseases and cholera following episodes of cyclones or droughts or flooding. And interesting, we found there was a fair bit of evidence documenting outbreaks of waterborne diseases like diarrheal diseases and cholera. Not so many links between extremes and malaria, and some emerging evidence about the impacts of things like droughts and extreme rainfall on dengue. And I will talk about some of those studies as we go through. So just as a reminder, I know this has been covered a lot in this course, just often when we're trying to understand the impacts of El Niño on infectious diseases, we want to understand how historical changes in the sea surface temperatures may have been associated with outbreaks of these diseases. So this is just giving us a reminder of the different areas of the Pacific Ocean where we can monitor the anomalies in the sea surface temperature and remind ourselves as when we've experienced these large El Nino events, for example, in '98, and also 2015 to 16, and this year we are seeing. This is the projection. This is a forecast from ECMWF showing a plume for anomaly plume for the Nino 3.4. And we can see that according to this, we would expect the sea surface temperatures in the Pacific Ocean in the Nino 3.4 region to a peak in somewhere between December and February. And this has implications for impacting the climate across the globe in different ways and at different lead times. So, for example, when we see warming of the sea surface temperatures, this tends to be associated with particularly warm conditions in different parts of the globe. So here we're looking at the correlation between December, January, February sea surface temperatures when these El Nino events tend to peak. And this is looking at temperature across the globe. So we can see that particularly when El Nino peaks, we can see warming, for example, in the north of South America, particularly along the coastal areas. And then that tends to drop off as you go through the season. And also for precipitation, we actually tend to see, for example, if we focus on South America, we can see in southern Brazil, northern Argentina, we tend to see exceptionally wet conditions during El Nino events, which can often lead to flooding, whereas in the north of Brazil and northern South America, we tend to see more dry conditions. So this has implications for how we may use this kind of information to try and understand the risk of outbreaks of infectious diseases. So this is an image of the supercomputer that we have at the Barcelona Supercomputing Centre. I joined the institution last year and established the Global Health Resilience Group. And we work alongside the Earth System Services Group to incorporate climate information, including forecasts and projections, into decision support systems to provide information for public health decision makers, particularly to build resilience against climate-sensitive infectious diseases. And we work across several different spatial domains, time horizons, and disciplines. So, for example, we develop indicators at the global level to try and understand how the climate has been impacting health over the last few decades. We also work with ministries of health and environment agencies at both the regional and national level, trying to incorporate forecasts into early warning systems. And we're also working with local decision makers to see how we can incorporate finer scale data, both for environmental monitoring and disease surveillance data from, say, weather sensors and drones, to really understand these fine scale processes and how they can impact disease risk. And we're also working to try and incorporate these concepts of risk that are used by the IPCC in terms of measuring risk in terms of hazard, exposure, and vulnerability with the One Health approach to understanding how the environment, human and animal health all interact to impact the health of the planet and people. So this is just a snapshot of some of the different projects we're working on in the Global Health Resilience Group. So we've been working on incorporating different data streams, including Earth observations, disease surveillance data, and seasonal forecasts into Bayesian statistical models to make probabilistic forecasts about dengue. We've had some particular success at doing this, for example, in Vietnam. We also have projects looking at harmonize different data types to be able to build a robust evidence base so we can develop early warning systems and health vulnerability assessments. We have been developing modelling tools to be able to understand the compound impact of extreme climatic events. So, for example, if we're in an area where we're experiencing a drought and then a flood, how might this impact the risk of different kinds of infectious diseases? And we're currently leading the Lancet countdown for Europe, which tracks the impacts of climate change on health and the co-benefits of climate action, to try and make policymakers aware of the urgent need to develop tools to mitigate the impacts of climate change for health. And our goal is to try and translate all this information that's available at our fingertips from satellites, from gridded products, from forecasting models, and trying to translate this into indicators that are useful and actionable on the ground, which can help pinpoint interventions such as mosquito control or educational campaigns with some lead time. So I'm just going to explain about some of the work that we've done over the last few years in collaboration with my colleague, Dr. Ana Stewart-Ibarra, and other collaborators, and trying to understand the impacts of El Niño on dengue in Ecuador. So this is an example, this is an image to show the extreme flooding that was experienced in the southern coastal city of Machala. This was in February 2016, and this was one of the worst flooding events that had been experienced in the city since the previous El Niño event in 1998. And this, of course, has implications for the transmission of many different vector-borne and zoonotic diseases. So we were working with partners in Ecuador to collate the different disease surveillance data for dengue cases from 2002 through to 2015 with the meteorological station data to monitor changes in precipitation and temperature. And also we compared this to the Oceanic Niño Index. And we could see some general patterns, like when we get El Niño, we tend to see warmer and wetter conditions. And this tends to be associated with outbreaks of infectious diseases. So we combine this information into a Bayesian hierarchical model, which also accounted for seasonality and interannual variation that could be attributed to other non-climatic factors. And then we combined this model with different data streams to try and predict the evolution of the dengue season in 2016. So this is just showing us what's known as the endemic channel. So this is just the mean and upper 95% confidence interval of the historic dengue cases for the 5 years prior to the year that we were trying to forecast. So if we were to rely on current practice, then we would expect in 2016 to have seen a peak in dengue in around June. And then using a climate-informed dengue prediction model, we predicted a slightly earlier peak in March with an 85% chance of exceeding the 95th upper confidence interval over the previous 5 years. And then after the event, we compared this with what the data was actually observed, and we could see that there was in fact an earlier peak this year. So what helped us be able to produce this prediction was, first of all, using an ensemble of seasonal climate forecasts for both precipitation and temperature. We can see here that this year that most of the ensemble members were able to pick up this exceptionally wet event that happened in February, which coincided with the flooding event image that I showed you. We can see here the dashed black line is showing the actual observed precipitation that was measured in the city of Machala. And also temperature was also predicted to be higher than usual. So this helped us predict the timing of the peak, and also the magnitude of the dengue event was improved because we were able to incorporate some data from an active surveillance study that was conducted, which actually found that in the previous year, around 70% of the dengue cases that had been reported were in fact chikungunya. So this also had slightly distorted the endemic channel. So this information also helped us more accurately capture the magnitude. And another interesting aspect of this study was the way that we were trying to align the seasonal climate forecast information with our meteorological station data. Because if we were to take the forecast from the grid square in which the city and the meteorological stations are included, then we would have been predicting temperatures that are systematically cooler than the ones that are actually experienced in the city. So in this study, it made sense to use data from a grid square just next to the city over the ocean, because this was more aligned. So this is a very sort of simplistic form of bias correction. We've also been working with colleagues in Argentina to understand how El Niño and flooding events are associated with leptospirosis outbreaks. So we published a study this year where we were developing a two-stage approach where we were making initial outbreak predictions, first of all, just using the El Niño indicator and the lags that we found between these anomalous sea surface temperatures associated with El Niño and lepto outbreaks. So in a first stage model, using the El Niño indicator alone and accounting for the seasonality and interannual variation, if we were to have made a prediction in December for March, we would have found a probability of an 84% increase in the risk of lepto outbreaks. And then 2 months later, if we make a subsequent prediction using precipitation and river height, then this probability outbreak would have been updated to 89%. So this framework is particularly useful in a setting where, rather than having to fall back on using forecast information, we can use the lags in the system to provide these early indicators. I'm going to talk now a little bit about some of the work that we've been developing over the years in the Caribbean, working with partners at the Caribbean Institute for Meteorology and Hydrology and the Caribbean Public Health Agency to try and understand how we can better use climate information to provide climate services for health. Here, we are looking at the dengue incidence rate that was observed in Barbados from 1999 to 2016, and comparing this with the standardized precipitation index, which can tell us about the severity of either drought events or exceptionally wet conditions, where negative values are indicative of drought and positive values are indicative of extremely wet conditions. And also we found that it's well known that in the Caribbean, in Barbados, the drought conditions are very much linked to El Niño events. So when we have these strong El Niño events, we also tend to see exceptionally dry conditions. And it had been noted by our partners in Barbados that the changes in the dengue epidemiology, and they were starting to see outbreaks of dengue potentially associated with drought conditions. And they thought that this might be due to the recommendation to store water during drought conditions, which might be leading to an increase in mosquito breeding sites. So we extended the approach that we had developed in Ecuador to try and understand the delayed and non-linear impacts of both the drought indicator and temperature. And we found this interesting patterns where several months after drought events, we saw an increased risk of dengue outbreaks, but also immediately after exceptionally wet conditions. And in terms of temperature, we found what you would expect from the literature, that several months after particularly warm conditions, we found an increased risk of dengue. So we combined all this information into a model, and using out of sample predictions, we had a look at how well this model could have predicted the probability of an outbreak. So here we're just looking at the shading color is telling us the probability of an outbreak according to our model. So the stronger the color of purple, the more probable it would have been. And then the X's are marking if an outbreak actually occurred. So the outbreak is defined as exceeding the 75th percentile of the historical distribution for any given month. And we decided that with our partners in Barbados that we would trigger an alert if that probability exceeded 30%. So that was based on a separate ROC analysis. So here we can see how this model compared to a baseline model. So the baseline model is including just a term to account for that seasonality alone. So we can see that the climate-informed model produced more hits and less false alarms compared to this baseline model. And these findings were, at least in a qualitative way, incorporated into the Caribbean Health Climatic Bulletin. So during a drought event that was observed in 2020, followed by a forecast for exceptionally wet and warm conditions, then a warning was provided about being aware of trying to eliminate mosquito breeding sites. Okay, and we've also been developing a body of work trying to understand how we can incorporate climatic information and socioeconomic indicators into dengue early warning systems in Brazil. Following on from our work in Barbados, we were really interested to see if this association between droughts and dengue might also hold in a larger geographical area. So here we're looking at the dengue incidence rate across the whole of Brazil. We can see there's over 3 million cases of dengue reported over a 20-year period between 2000 and 2020. And we compared this to, here we were using the Palmer Drought Severity Index. And we can see that over the last few years, we've seen particularly severe drought conditions in the north and northeast of the country in later years. And we were very interested to find a very similar pattern where around 3 to 5 months following drought events, we saw this increased risk of dengue in Brazil, and also immediately after exceptionally wet conditions. And we wanted to know how this would interact with the underlying landscape. So we looked at how these patterns changed according to if you were in a particularly urbanized area, or also areas with increased water shortage reports. And we found that this drought effect was in fact exacerbated in the urban areas, whereas the exceptionally wet conditions were exacerbated in the more rural areas. So this has implications for designing early warning systems depending on if you're operating in an urban via rural setting, and thinking about which indicators are most important depending on your setting. And this is some work that we're developing with the Red Cross. And again, it's important to think about when seasonal climate forecasts may be able to offer more skill and more useful information. So we know that seasonal climate forecasts tend to be more skillful when we have these El Niño events, and that can help us inform our models depending on where we are. Here we just we can see across Brazil that when we do tend to get El Niño events, that is more associated with droughts, whereas in the south of Brazil and also in northern Argentina, the El Niño events are more associated with exceptionally wet conditions and flooding. So again, we must take this into consideration when we're developing disease-specific models in different geographical locations. So of course, all these models depend on the kind of information that you are inputting into them. And so we're currently working on a project to harmonize multi-source, multi-scale data with stakeholders operating in different areas in Latin America and the Caribbean. So we're working with partners in Brazil, the Dominican Republic, Peru, and Colombia to try and develop toolkits to gather different kinds of data from satellite images, gridded climate reanalysis and forecasts, and to be able to integrate this with strategically collected data from drones and weather sensors, along with surveillance data from socioeconomic, demographic, and health system indicators, and disease surveillance data. So in particular hotspots, for example, in cities, the Amazon rainforest, small islands, and highlands, we can build tools that can help address the problems that are particularly prominent in those areas. So if you'd like to learn more about this project, we now have our website, which is live, and we have several news stories and information about our different partners and projects. So please do visit the website. And we also have a new project called ID Extremes, where we're working to develop modeling tools to try and incorporate different climatic indicators and develop these impact-based forecasting tools for health. And taking advantage of the current infrastructure that exists at the Barcelona Supercomputing Centre, we're building an R package tool that will sit alongside the suite of other tools that have been developed by the Earth Sciences Department to process climate indicators, to be able to verify climatic information, And then our tool will help use this verified and bias-corrected information to provide useful probabilistic outputs for infectious diseases in partnership with users in different countries. We're particularly working with the Barbados Meteorological Service, the InfoDengue platform in Brazil, and we're also working with the Red Cross and MSF to try and incorporate this kind of information into their dashboards and user interfaces with different partners in Africa and Southeast Asia. And taking advantage of the current emerging situation with El Nino and demand from our partners in several countries across Latin America and the Caribbean, we're currently developing a series of models to try and estimate the probability of outbreaks given different combination of climatic indicators, using a combination of observed and forecast variables for a range of different countries. So we're particularly focusing on Barbados, Ecuador, and Northern Argentina in the first instance, and to try and develop a forecasting scheme where in a given month we can make probabilistic predictions from 1 to 6 months in advance using different combinations of observed and forecast information. And we hope to be able to share these forecasts and updates with our partners and the community in the next few months. So please watch this space. We're also in the Global Health Resilience team and the Data and Diagnostics team looking for a postdoctoral researcher and a software engineer to help us develop these different projects. So please, if you're interested in joining us, please do get in touch. And if you'd like to hear more about some of our projects, there's a short video that was produced a couple of years ago by the Royal Society, which includes some interviews with some of our partners in these different hotspots. And I'll be very happy to pass over to my partner, Ángel, who will be giving the next talk. Thank you very much.
Thank you so much. Thank you, Rachel, and hello, everyone. Are there any questions for Rachel before I start, or how? Sorry that I arrived a few minutes late and I don't know if this was discussed.
Hola, buenos días.
¿Qué tal? Buen día.
Sí, bueno, primero agradecerle a Rachel por su presentación. Gracias, muy informativo y muy remarcable lo de las alertas tempranas y todas las presiones para tener un pronóstico de enfermedades zoonóticas y por de vectores. Las preguntas se realizarán al final de la sesión, entonces les daremos paso a nuestro segundo panelista. Por favor,
so now we'll give the floor to our second speaker.
Perfecto.
Ángel. Thank you. Can you see the screen?
Perfecto. So,
perfect.
This is a talking in English, correct? I can do it either way. If you don't ask me to speak Chinese, I can do it. So it's a pleasure to be here. Thank you very much for the opportunity. So I'm going to show a few slides, and then I think that the best is to actually try the tool, a live demo, so we can, I don't know, I'm going to ask you to mention a location, and then we will take a look at what this tool can do, okay? So I'm going to be talking about Aedes. You will, well, I think that you all know what Aedes is in terms of a species, but this is a climate and health service that we had been building for years with PAHO and many, many others. You will see them in a second. So the outline of my talk is I'm going to talk a little bit about context, about this demand-driven approach, which is so essential when we want to do climate services. And then I'm going to introduce the tool, and then we will actually play a little bit with it. So this work comes from a long story of collaborations with several partners, in particular with the Pan American Health Organization, the World Health Organization. And originally, well, we have been doing prediction for a while, and these partners came and asked us if we were able to say something about the Zika virus, probably, especially people in Latin America who are here in this call right now, will remember that this was a big thing a few years back. So we actually published that paper on seeing if we could have been forecast we could have been able to forecast the Zika epidemic. So you will see a little bit why, in a second, why that's so important, because it's through these collaborations with real world decision makers and how they actually make decisions that defines absolutely everything that we need in order to create these type of predictive tools. So, the typical common demands questions that we find out there is something like, can we forecast Aedes-borne diseases? And, this is similar to this question I just mentioned coming from PAHO in terms of Zika. And what's going on? Okay. And also, we learned very early that they have protocols in place that tell them what to do depending on particular values, on particular thresholds of their key variables. So what if I just provide the mean or the expected median in a particular forecast? It's like we provide that to them and they compare it to their protocols. And the protocol says, if these values exceeded, do this. And if these other values exceeded, do that. And those values in general are not going to agree, are not going to be equal to the mean or the median. So we needed to go beyond that, okay? So as you can imagine, there are a lot of people leading and involving Aedes, this beautiful project. I am so happy that it's female-dominated. So Laura Harrington from Cornell, I was at that time at Columbia University, now the Barcelona Supercomputing Center, Patrick Keeney from University of Boston. I cannot mention all of them, but in particular, Carmen Gonzalez-Romero now at BSC and Laurel Dicero have been essential for this work, more if you want on the model prediction side of things. And then Anna Rivière-Cinnamon from PAHO, WHO, and of course, Madeleine Thompson, Wellcome Trust. So it's a lot of people and a lot of institutions that I am mentioning here. We got also funding from NOAA to do this system. And it has been published. If you want all the methodological details, you have that paper over there that was published in 2020, and we have several others that we can share. And the system has been so successful, has been operational since the end of 2019. Operational means that every month you get a real forecast for the next 3 months. So this is not just a paper, it's something that we have there active and has been running for a few years now. And we want to upgrade that with Rachel's team, and a lot of interactions that are happening right now to expand into Europe. But let me show you what this is. So Aedes is this Aedes-borne disease environmental suitability monitoring and prediction system. It's a climate service, so it's supposed to serve, it's supposed to help decision makers to make the best decisions possible. So the interface, we'll play a little bit with that. We'll have a map showing some colors that are related to the particular number, the particular variable that PAHO WHO, the World Health Organization, asked us to use. It's not dengue cases, it's not temperature, it's not rainfall. They wanted this R0, which is the same type of variable number that was used during the COVID time to make predictions. So it's very similar to that, methodological approach. And you will see that there is also information in context. What does this prediction mean? We will play with that in a little bit, and it will be, these lines and that you're seeing over there. So, but let me advance. So as you can imagine, it has, this is a very complex problem because you need on one side to pay attention to everything that is happening in terms of climate, not only El Niño, because El Niño is very important, but it's not the only player. Imagine that climate is a symphony and you have multiple instruments playing that symphony. Climate change is one or a set of instruments in your orchestra. And then you have El Niño, and then you have things happening in the Atlantic Ocean, in different regions of the Atlantic Ocean, and also over land. So we need to pay attention to, in order to capture and listen to the music, probably you all, or most of you already watched this movie Oppenheimer, and there is this question of, can you hear the music? We hear the music, and the music is not only coming from El Niño. So because it's so complicated, not only in terms of climate, but also when you include the presence of the mosquitoes, to know if the disease is circulating or not, and then to try to say something about the environmental conditions there are, an envelope for it all, the thing is really complicated. Okay, but we found that if we focus on environmental suitability, which is the goal of the forecast system of what ICREA is going to be forecasting is going to be related to environmental suitability, we were able to satisfy the demand coming from the decision maker, in this case, PAHO. So you're going to see this map later. The way we define R0, some of you probably already know about that, but it's as the number of cases or secondary cases from each primary case. And this will be, the traditional definition of R0. And although it's not, it's very theoretical, it actually has been used to develop these protocols that I had mentioned. So basically, R0 is giving us a measure, some people say it's a measure of the risk, because depending on that number, I will have an idea of how many secondary or tertiary or whatever the generation is cases I'm going to get from each one of the original ones that was, put into a community that is assumed, this is why I say it's theoretical, because it's not true, it's assumed to be completely susceptible to that disease. So how this works? Because no model is perfect, we use a multi-model ensemble. What that means is that we use different eco-epidemiological or ento-epidemiological models to assess R0. So each one has its own pros and cons. Nothing is perfect because, as we all know, life is hard. So we use 4 of these well-tested, well-known in the literature, like robust model for the ento-epidemiological component of what we want to do. Remember the different boxes that I just showed you? And we have a combination of those 4 models that we call a multi-model ensemble. But those models will need not only ento-epidemiological information, will also need environmental information. So when we feed those models with observations, we have a monitoring system. When we feed those models with forecasts, we have a forecast system. So we need to be very aware of how to do this. And because no model is perfect, we'll need to do a lot of these calibration corrections that Rachel was mentioning a few minutes ago. So once you have that, you have at the same time a monitoring system and a prediction system that is consistent, because we're using basically apples and apples to be able to say things about that. So it's actually what is called in the literature super ensemble, because we have multiple climate models being fed into multiple epidemiological models. So at the end of the day, we needed to work with more than 4,500 of these simulations in order to assess how good that is. So we learned that actually using multiple models is important. What you can see here on the left, this is it's a metric to assess how good the model is. The closer to 100, the better. If we use any model, just one model, any model of those, it will be this good. Once we combine all of them, we get the best of every single one, and we get increased predictive capacity. You will hear that here and there as skill. When we say skill, is how good a model predicts something with respect to something. That something is measured by this particular metric here, but that's not important. The important thing is that PAHO told us that we needed to give them the expected value of R0. Okay, this is what for a particular season was observed. This is coming from the paper. So I don't remember if this was 2018 or something like that, whatever that was. And this is what happened. But something important was this discussion about nothing is perfect. We will give you the expected value for each location and an error bar. That error bar is here plotted in this additional map. So the way you understand this is that you need to get the actual value plus minus this map. There is no way we can only give you this because no forecast is perfect, okay? So we assessed that for multiple years and to see how good the model is. And we found that the model was better in this particular season than in that other season, that it was better in this particular location than in that other one. And all that has been reported in that paper. So if you want to see the details, we can talk about that later or read the paper. But the other important thing is that they wanted all ranges of possible thresholds in their protocols. There was no way for us to only give the median or the mean, because they had something like, if this is particular location and I exceed an R0 of 3.2, I should do this or I should do that. So you see here, this is the demand. They say 3.2. The blue one is what typically happens on average for 30 years. So 3.2 is exceeded for that particular location 60% of the times. And in that particular forecast, 3.2, that magical number that triggers this set of actions, but not this other one, was like the probability of exceeding that threshold was very high. And these are those two locations. In D, we have New York, and in C, we have Miami. And you can see that simultaneously that provided information to decision makers to see, to PAHO in this case, to see, what to expect, not only, to follow the protocol, but also to be able to translate that in terms of people that needed to go to this location and not that one, because the forecast system was suggesting to be, that location would be worst. I'm going to stop here with my slides, so I don't know if I still have like at least 2 or 3 more minutes. If not, just let me know. But this is how it looks like the latest forecast that has been produced by the system this month. So it's October 2023. We already produced November, December 2023. Sorry, this is January 2024. This is a mistake that I'm going to fix right now. Apologies. Good. Nothing happened. So November 2023, December 2023, and January 2024. And again, what we're seeing here is going to be for one particular location that you can see there in that red dot. That is in Colombia. Probably we have some Colombian people here, Barranquilla. And we have what is the typical behavior in terms of rainfall, frequency of rainfall, frequency of rainy days, temperature, the average, the maximum and the minimum, and the range, because all these were requested by the decision maker, by PAHO, as important information. For example, if we know that this season usually rains a lot, do not do the fumigation, the vector control with chemicals, because the rain will clean everything and then you will need to do it again. So all that was considered. And this environmental suitability. In bars, you have what usually happens, that means average of the last 30 years. And in black, what has been happening this particular year and what we expect to happen. Do I have 2 minutes? I'm still in the minutes. So this is the interface, okay? So I will...
Si puedes hablar un poco más, Ángel, si es que...
You can. You do have a few more minutes if you want to.
Solo por mostrar...
Great, awesome. I wanted to show how it works.
Just to be consistent, I'm going to go back to English. So I have been granted 3 more minutes or whatever that is. So this is a map, because as I said before, you as the Minister of Health in a particular country might want to know where to focus your money, your attention for the next 3 months, okay? See, this is April. Why I'm doing this? To show you how good the system is. The black line is
Ángel.
Oh, yes.
Sorry, Ángel, we can't see the map. We can just see your summary slide.
Oh, okay, thank you. What about now? Yes?
Great, thank you.
Oh, yeah, thank you so much. I was like, talking to myself, sorry. Okay, so this is a map showing you the distribution of the forecast of the expected value of that magical number that they use for the protocols. If that is dengue cases, you use dengue cases. If that is temperature square minus precipitation divided by relative humidity, that's what you need to do, okay? In this case, they wanted R0, which is the same quantity that we also use for COVID. This is not a COVID model. This is a iris-borne disease set of models, okay? So we see that regions in red and even like purple or pink should require more attention from the authorities, from the decision makers. And I'm saying that this one is here for April 2023, because I want you to see how the forecast, which is here in red, probably you can see my mouse right now, my cursor. And remember, black is what happened this year. So let's see how good our forecast for this particular location in Barranquilla, has been. So that was April. So then that's May. Okay, that is June. So let me go back. You can see that the red line is not exactly on top of the observation, but is pretty much like over there, like in this case. Remember that these are seasonal forecasts, so this is a 3-month. So we're comparing like the middle what you're seeing here is the observation at monthly time scale. So we are not comparing like 3 months and 3 months. That will be a fair comparison, and then it will be even closer, even better. But the red line is actually following that. So for details on the evaluation of the model, let's talk later or read the paper. And what is happening now? So this is what we had in August, September, and this is our latest forecast for October. Dun, 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 dun. So, this line is now shorter because the other extreme is on next year, is on January 2024. So that's why the size is a little bit different. But this is what happened, what we expect for this particular location, Barranquilla. And with that, they can say, oh, so is exceeding or not the threshold in my protocol? This is what I need to do now or not. And you can zoom out. And you have the entire, well, this is a particular domain that since NOAA funded this project, they wanted to see this particular region because that's of interest for the US, but also for when people want to do vacations near the US. So they call that the transboundary region. But let me show you a couple of extra things. They wanted for us to produce information about the exposure. So where is the population? So the map room also has that information. You have information about the hazard, the R naught, the dengue, but also about where people is. Because if this location over here is super red, but no one is living there, so then I can relax. So there is information about exposure. There is information about vulnerability. They said, following some studies from the CIA, that infant mortality rate is a robust measure of vulnerability, even for disease, for basically a lot of multiple variables, but in particular for diseases like the ones we were interested. Okay, so you have here infant mortality rate, and you also can see precipitation and forecast predictions, if that's what you wanted. They consider that useful, but also this is the monitor. This is, remember that I told you, don't tell me that it's not going to load. Remember that I told you that we can observe data in the system. So this is what has been happening. I can do something crazy here, something like 2000 or actually 2020. And it will load with observations. Tell me yes, tell me yes. Let's do it. Why are you shy? And it will load into the system the observations and show me like the evolution. I will be able to see that August tends to be like warming in the north, so then I have more environmental suitability for those diseases over there. Okay, so what is going on right now? Now when I need you, you are not going to appear. So, right now it's computing. Oh yeah, so it's just being shy, 2010. So this helps to provide context. If I tell you it's gonna rain 200 millimeters tomorrow, that means absolutely nothing until I tell you typically it rains 100, or typically it rains 2 millimeters. So 200 is the end of the world. I always need context, and this is designed to provide that context. Okay, so I'm going to stop there. There are a lot of other things that we might be able to do that is related to this plot that I mentioned. Let me just go back to forecast and to the last one that we had, which was, I think, Barranquilla. For mortality rate, I think it was this one. So see, here at the end, we have that plot for Barranquilla. This was produced in October for November, December 2023, January 2024. And you select the demand, you select the threshold for your protocol, and then it tells you what is the probability. Blue is the average from the last 30 years. For example, 3.6 usually has not happened. And now, because of climate change and natural climate variability, because of this influence between climate change and everything else in the climate symphony that is not climate change, that is there, that is natural, we see that now those probabilities have been enhanced. And 3.6 now was 0%, and now it's 10%. So this is already a lot. And I'm going to stop there because I imagine that you have tons of questions. Thank you very much, and this is it. Oh, everyone fell asleep. No, Rachel is awake. Good.
Good.
We have more people awake.
Bueno, muchas gracias, Ángel, por tu presentación.
Well, thank you so much, Ángel, for your presentation. It was quite informative and highlighting the relevance of the models and what you have been working on. I also like that it's also taken into account that these are probabilities, that there's a margin for error, but this is very useful to use for forecasts in the region. And also the AIDIS project is so interesting. I would like to review and read more on it. Well, I would like to begin now with your questions. I'm going to begin with Rachel. Right now, I'm going to switch to English. And you know you have interpretation with the button at the bottom of the page.
Is the epidemic channel different among countries and between the North and South Hemisphere?
Yeah, so usually each disease surveillance team calculate their own endemic channel based on the data observed in their place of interest. So it could be at the country level or regional level or even city level. So it's usually just calculated using the previous 5 years of data, sometimes longer, some places use 10 years, and often a bit of a qualitative decision is made when trying to calculate outbreak thresholds. Often by eye, outbreak years are removed, and then some kind of threshold is determined using maybe the mean or mean plus 2 standard deviation. So it's very place specific.
Okay, thank you. Well, here's a more local question, is for the Peru region. How useful is citizen science in alerting the presence of mosquitoes, of sharing mosquitoes-borne diseases? What is the reality of this region? Can citizens science help to combat these diseases? What barriers may exist to this? How well people are well educated to combat these diseases? In Peru, it seems that this is not happening, or is not happening as intensely as this should.
Yeah, I think citizen science can be an incredibly useful tool for many aspects of trying to control diseases. In terms of identifying mosquitoes, I've seen examples of it being particularly useful in emerging settings, being able to use citizen science to detect invasive mosquito species or a change in a particular species. We've been working with collaborators on a project called Mosquito Alert, which initially focused on the what's known as the tiger mosquito in Europe, which is the Aedes albopictus mosquito. But through this app, you're able to, through photos, detect different species. So this is like capable of detecting introductions of Aedes aegypti, for example, into Europe. So it could also be very useful in situations where you know, the mosquitoes are present all year round, potentially. I guess, yeah, its utility and where you have where it's ubiquitous in the environment may be less clear, but certainly using citizen science for any other aspect of sort of reporting symptoms or reporting breeding sites. I think these tools are incredibly useful when you're trying to really get sort of granular fine scale information and trying to target resources on a very local level. So I think for certainly a lot of scope to incorporate citizen science in these kind of decision support tools.
Okay, good information. Thank you. The next one is, in reference to clinical symptoms of dengue and leptorrhiosis, many times only the laboratory test for dengue is done, leaving aside the test of leptorrhiosis. Therefore, many cases remain in a situation of probable dengue. What is the probability of confirming the clinical symptoms of leptorrhiosis and requesting the laboratory test for leptorrhiosis? Can a patient have both diseases at the same time?
Well, it is possible to have co-infection with both. So the lepto data does need to be laboratory confirmed, but there's also many times dengue is also confirmed based on sort of clinical presentations rather than laboratory, so you can get misreporting in both directions. So in areas where leptospirosis is particularly prevalent, for example, in areas with lots of agricultural work or flooding, then potentially the health services may be more aware to conduct a test for leptospirosis. But I imagine there's a lot, I don't have the statistics to hand, but I imagine there's a lot of misreporting between the two diseases.
Okay, well, that remarks the importance of a well-trained health system for identifying this. Well, I think, are there any studies on the impact of pregnant women affected by dengue, malaria? What measures to take for this?
That's not really my area of expertise, but there certainly is a lot of literature looking at pregnant women are definitely a very vulnerable group when it comes to infection with malaria or dengue. There's certainly been a lot of research looking at this for Zika infections as well, but I don't really have much more information on that at the moment.
Well, okay. Well, thank you, Rachel. I will jump now with Ángel.
May I add something to that one?
Yes, sure.
Yeah, so this is very, very important, especially in terms of even some other forecasts that we have for undernutrition in Central America, because, as we all know, it's very, very important that the iron levels in pregnant women are at are within a particular range. And diseases like malaria or dengue are key because it might lower their iron levels. And although it's not very common and there is no, in general, way to be worried about this, there have been reports in some cases death by a combination of factors involving the person having malaria or dengue. So again, as Rachel said, this is not my area of expertise, but we did some work about it relating this compound hazards, health hazards involving undernutrition and dengue, and even it impacts. It's very important in developing countries, for example, in Central America, because a lot of women won't go to the fields, and that will impact even the agricultural activity in those countries. So it's a very interesting case of compound hazards that still needs to be further investigated.
Good, thank you for your response. Rachel, I have another question for you. How do the models discriminate the expansion of dengue due to the behavior of meteorological variables of transmission due to the mobility of sick people? In recent years, there has been a very significant increase in the migration of people from tropical regions to mid-latitudes. Many of these people arrive with illnesses.
Well, in the terms of the work that we were doing in Brazil, we were looking at sort of erosion, if you like, of these diffusion barriers. So looking at things like the length of the transmission season, also connectivity between different places, and the role of different urban centres. So whether you're in a metropolis compared to a regional capital, and how connected those areas were. And we found that a combination of factors, including more months in the year with suitable temperatures, being sort of connected to a regional centre, having experienced an outbreak in the previous years, were indicators to show the expansion of the dengue transmission zone into lower latitudes and also higher altitudes. In terms of sort of international travel and expansion into previously unaffected areas. There's certainly many efforts to try and understand how connected, for example, places in Europe are with areas experiencing endemic diseases, and being able to connect data on travel medicine and report imported cases with the prevalence of mosquitoes, and trying to combine these different sources of information so that the public services are aware when there is an increase in imported cases, there is the suitable conditions for the mosquito, to be able to sort of deploy any prevention measures to make sure there's no onward transmission.
Okay. So here's the last question. How do you work with communities to share the risk and prevention measures?
Well, particularly in the project that I mentioned called Harmonize, we have a community engagement component of that project where we're working with different community members in the hotspots we're working, so particularly in the Brazilian Amazon, in the Colombian Andes, and also in rural and urban areas in the Peruvian Amazon. And we're working with local community groups to really understand the perceptions about how climate variation, climate change has been impacting sort of changes in the epidemiology and outbreaks of different diseases over the years, and to think about different adaptation measures that can be adopted to try and build resilience, and also to make sure that in those communities they feel comfortable having novel technologies or things like drones in their environments to collect data, and to make sure that there's sort of a mutual understanding on how this kind of data can be used to serve the needs of the local communities.
Good. Thank you. Thank you for that. Well, now I will jump with Ángel. Well, we have a few questions. So for Latin America, this comes from Latin America. In the areas of Latin America with droughts, but due to heavy rains upstream in other areas within the same basin, flooding occurs downstream hundreds of kilometers away. Right now, flooding is occurring in urban areas of Uruguay due to rain that occurred in the south of Brazil. The increase in dangers, risk, and vulnerability is evident. However, the situation has left out of the climate and health predictions since flooding has not been contemplated. Wouldn't it be convenient to include flood models in the multimodal combination?
Yeah, I'm on mute. No, yeah, very good question. Thank you actually for a very detailed background for your question. Yeah, that will be of interest. I'm gonna say actually that is related to the threshold question that we were discussing before. So at the end, you are talking about particular thresholds that are extreme, for extreme rainfall events, and also related to floods. And there are obviously multiple types of flood, fast floods against like more like slow motion floods. And those thresholds need to be considered as an input when we are like doing our models and our forecasts. So I completely agree with you, especially in those locations you are discussing. So yes, thank you for the questions. And my short answer is yes.
Okay, well, here's the next question. No, let me see. I'm sorry.
No worries.
I think maybe we can switch to Spanish. Is fine.
Yeah, lo que sea está bien, y he respondido un montón en el chat.
Yes, I've answered too many questions in the chat, so if I don't have more questions from you, I won't cry. Okay, we'll go back to Spanish then. The tool you presented, Ángel, is it being used in countries in the region? How much is it being used? This question comes from Peru. It's mainly used. Let me just share something with you so you can understand this with more context. So the geographic domain that was covered is this one. As you can see, Latin America and the Caribbean, we have this area. So the issue with this is that I've been asked in the chat, for example, for Peru, what do we have? At the moment, this is what we have. And that's because of the definition of the initial project. So it's mainly being used in this region, and it's being used by PAHO. And this is very important because PAHO said that they are the ruling entity for meteorological matters. So they wanted to do the translation of that information that can be quite technical for the general public. And they wanted to upload that information into their bulletins. So PAHO is using that information. Ana Rivière Cinnamon from PAHO, who's a co-leader of this process. She's now the chief of the PAHO office in Panama. So they're using this information at that level, at the general office level, and also in Washington. So, as I was also mentioning in the chat, they're interested in having a second version with some methodology improvements and other models that cover the entire Latin America. So the question whether it's being used in other countries in South America, besides Colombia, as far as I know, it's not being used outside of PAHO. And in Colombia, besides PAHO, there is the Health Institute that is also using the tool. And as far as I know, it's also being used in Panama.
Uy, ¿lo perdí? No, Rachel está ahí, así que... Vale.
I see, Rachel. Something happened. Jose Martin says, thank you for the question. And thank you. The PAHO contact point in Panama is Ana Rivière Cinnamon. I'm going to write it down. I'm also answering a question in the chat about the forecast capacity. We could link this to another question, whether there are
las enfermedades de vectores en América Latina.
It's a big question. Yes, there are. That is why we have vector control activities, and that's why we have this continuous surveillance efforts. So the short answer would be yes, of course, we have protocols. In some areas, they're more efficient than in others. In some countries, there's less harmonized contexts. In some countries, depending on the state or province, however you call it, there is a different surveillance system, which is interesting. And also in some regions in the Caribbean, each island has its own surveillance system, but the protocols exist. We could link that to two questions, that we can merge it into one. In the model, are you considering the fact that there is more resistance of dengue mosquitoes to fumigation? I don't know if that is a question for me or Rachel, because we work with a cocktail of models, but the one we use in ADIS doesn't include that type of intervention. It's something that we would like to explore in the future. We're going to do an upgrade to version 2 that will improve some key aspects that will involve...
En una versión posterior es que pudiéramos incluir este tipo de intervenciones que son fundamentales. Y si me permite, son fundamentales porque...
And there are these factors that are very good as they introduce a loop that is important for the modeling. For example, if we say this is going to occur, if someone intervenes or takes action, there is going to be a change in the result. So that is something that is very hard to model. It's easier always to do modeling about the past, post-mortem, of course, that predicting the future. I don't know if that helps to answer the question. Another question is, are there forecasts for Brazil, specifically for the south of Brazil? As I was explaining in the chat,
mucho más al norte, pero que en la versión 2, en estas conversaciones con Rachel, queremos tener toda Latinoamérica y el Caribe, o sea, tendremos todas las Américas.
A focus that is more concentrated on the Caribbean. For that, we would have the south of Europe, parts of Africa, and southeast of Asia. So it's going to be bigger. So until Africa and Europe are more in shape, I would say that things shouldn't take too long. In the model, do you use biological parameters besides meteorological parameters? Yes, if you remember, let me show you this. This part in green that talks about meteorological aspects, well, this has a lot to do with several vectors, well, mosquitoes. It has to do with information closely related to the disease and interaction with humans. Those are models created by research institutions that are going to be tested. Those are models that include all these interactions. And of course, we have these entoepidemiological factors. Thank you for that answer. And now I'm going to switch into Spanish or into English.
This will be a question for both of you. Rachel, too, please, if you can reply something. How to understand these relationships between climate and vectors? What has been weakened and strengthened in the life chain of the actors involved, human beings and vectors?
I think that, information we can get about the climate in terms of climate variability, extreme events, and climate change, they have different impacts on the pathogens, the hosts, and the vectors. So it's really, we need to sort of understand how both the climate changes human behavior, how it also changes the biology of the vectors, and also interactions between the vectors, the pathogens, and the host. So that's why we're trying to move towards trying to understand this in this integrated One Health framework, so we can incorporate different sources of data to understand how climate is impacting all different aspects of health and the transmission of these diseases.
Okay.
I completely agree with Rachel. I don't think I can. So it's very important that we are aware of the complexities and how difficult it is, even as I mentioned before, to monitor, to address, to have good surveillance systems, and even more complicated, to have good forecasts. But a lot of effort is invested in having information that, although is not perfect, is actionable. That's what we are aiming at. We are not aiming at perfection. We're aiming at something that is really good, so you can have the best decision possible. If we aim at perfection, we will never actually get there. And with everything that is happening, not only regarding climate, but even this global world and a lot of socioeconomic variables, there are a lot of components that are not predictable. So I completely agree with Rachel.
Okay, well, thank you very much. Thank you very much for your presentations. This information here is very helpful for the region. And we also appreciate the presence of our participants here. So we will finish this session. Thank you very much, all of you. And well, I would like to remember the participants that we will have, we will reply actually the rest of questions in the website. So you will have the material to download them. And well, thank you very much for all of you. Thank you.
Thank you.
Have a nice day. Thank you.
Thank you.